An 80-kilogram construction worker sits down 2 meters from the end of a 1,450-kilogram steel beam to check his phone. What is the tension in the support cable? So this is a static equilibrium problem. We can see, at least we hope, that the steel beam and the worker remain at rest and do not move. So the basic concept here is static equilibrium. There are two conditions for static equilibrium. So the equations that we have at our disposal is the one that relates to linear motion. The net force acting on this system needs to be equal to 0. Also, the net torque acting on this system needs to be equal to 0. So those are two vector equations. One way to interpret that, and one perhaps simpler way to think about it, is to think of the up forces, the upward pointing forces, as adding up to be equal to the downward forces. So you might want to think of this as sum of the up forces equal to sum of the down forces. Likewise, the sum of the leftward pointing forces adds up to the sum of all the rightward pointing forces. And then lastly, for torques, assuming that you can just deal with motion in a single plane, you can interpret this as the counterclockwise torques add up to be equal to the clockwise torques. So there really are, for most of these kinds of static equilibrium problems, 3 equations to consider. We want to determine the tension in the cable, and so maybe one thing to do before we can apply these equations is to draw an extended free body diagram and figure out where the forces are acting and what we have to use to determine the answer. So let's draw this as simply as we can. There will be the beam, which has a length of 6 meters. The beam has mass, and so there will be a force acting on the beam. And I'll go ahead and draw that acting right here. Right in the middle, right in the center, because it's a uniform beam, we assume. So the force of gravity here would be the mass of the beam times g. Now the worker is sitting at a location that's 2 meters from the end, and by that we can assume that that's somewhere about here. That's 2 meters distance measured from the right end to the place where the worker is. We should indicate what the force is acting on the worker. Force of gravity acting on the worker is the mass of the worker times g. And the simple thing to do with this system is to not worry about the internal forces of the worker on the beam and the beam on the worker, because those cancel. The net result of all this is that the weight force acting on the worker makes the system want to be pushed downward. Lastly, or next, there's a force of tension that's being applied at this end. We can call that T, and that happens at an angle of 30 degrees. I'll call it theta for now. We'll let it be equal to 30 degrees. But then also, the way that this system is set up is that there's a wall or some surface that also applies a force. And I'm not sure how to draw it, so I'll kind of draw it generically like this. Let's call this F wall, indicating that it's providing some force which might be pointing up and might be pointing to the right. Now, as it turns out, we have enough information to determine both the tension force and the wall force. But all we're interested in is the tension force. And so what I would suggest is that if we tried to apply the F up equals F down equation or the F left equals F right equation, we would be stuck with having to deal with the force acting on the beam from the wall. The one condition that we won't need the force on the wall from is if we apply the net torque equals 0 condition. Let's see how that works out. We have to keep in mind that when computing torque, the torque computation allows us to choose, let's say, can be done, is done with arbitrary choice of axis. Now, that's true when you have static equilibrium. Basically, the axis should be the point that does not move, well, nothing here moves. And so we have a choice. The most intelligent choice to make would be to choose the axis to be right here. So we'll let the axis be there, do our computations. We could choose anywhere else, but this will be the simplest approach. With that choice, we can start to compute the clockwise and counterclockwise torque. Let's compute the clockwise torque. Notice that both of the weight forces are pulling down and making the beam want to spin in the clockwise direction. That's clockwise when we put the axis right there at the end. And so what we have to contend with is the various lever arms. We have this distance here, which is 3 meters. So the distance that I'll put in there is 3 meters. The force that I have to deal with is the mass of the beam times g. Now, where did I get that from? Let me remind you that the equation for torque is given by the distance from the axis to the point where the force is applied times the magnitude of that force times the sine of the angle between them. So what I should put here is a sine of an angle between them, but notice that is, in fact, 90 degrees. So sine of 90. I have to also include the torque provided by the weight of the worker. But notice that if this distance here is 2 meters, then this distance here, the distance from the axis to the worker, is 4 meters. So the relevant distance there is 4 meters. The force is the mass of the worker times g. The angle is sine. The angle is 90 degrees. Okay. So that is the expression that we have for the clockwise torque. When we go to compute the counterclockwise torque, we'll notice that the only thing we have to worry about is the tension force. The tension force wants to make it spin counterclockwise. The relevant distance there is the full length of the beam, 6 meters. The force is T, the tension force. The angle between them is sine. The angle is 30 degrees. Now, you could argue that the angle might actually be measured here, and you could call that 150 degrees. Well, it turns out that the sine of 30 degrees and the sine of 50 degrees are the same. That's always true. Whenever you have a computation that involves R and F, if you measure your angle here as theta or here as phi, you can use sine of phi or sine of theta, and you'll get the same result. Okay, finally, we can now apply our condition for net torque being equal to 0. What we have is 3 meters times the tension force. Where does that come from? Because this is 1/2. That's equal to the clockwise torque, which is 3 meters times 1450 kilograms times 9.8 meters per second squared, plus 4 meters times 80 kilograms times 9.8 meters per second squared. We've set the counterclockwise and clockwise torques equal. That allows us to solve for the tension. You should find the tension is about 15,000 newtons, or more accurately, 15,300 newtons for our final answer.